Okay, good afternoon. So only what, 50% or less than 50%? Uh, okay, so I believe some of your friends already go back home for Hari Raya. Okay, without informing me beforehand. It's okay. Probably some of your friends are still coming in a while. All right. So how are you guys doing with your Simon? Simon two? Got plan already? So afterwards, we want to see your plans so that because next week is already Raya, you can still show some progress lah, but online, maybe through email or WhatsApp. Okay, but not sure when I would reply that lah. Okay, so hopefully during tutorial after this, you can show us the floor plans so that we can approve, and then you can proceed with the next step lah in the assignment. Okay, so today's topic is about column. Okay, I know you have learned about columns in building construction 1, construction 2, right? But you have not, I believe you have not learned about calculation, how to determine the loads on column. Okay, so basically that's the difference between building structure and other subject, right? So in your assignment also, you need to one of the important things that you need to include in the assignment is columns, column analysis or column calculation. Okay, so that's why we have the topics today, right? So that you know what to do in the assignment. Okay, so bye. Okay, so I believe you know what columns are, right? So it's a structural member, usually inclined at 90 degrees on the on to the horizontal. Okay, so horizontal 90 degrees, right? Um, Carrying an axial compressive load. Okay, so it's different from a beam where it carries. What do you think beam carries? What kind of load? Huh? Sorry, tension, compression, something like bending, bending load. So basically, when the beam actually carries the load would actually bend the beam. Okay, but in columns, basically, the load would actually compress the beam because the load is carrying the load. So the column is carrying the load from above, and at the same time, you know that whatever forces coming on top, there is a reaction force from below, right? So basically, the reaction force from the ground would actually push up the column. At the same time, the load from the top, okay, pushing down the column. So that's why it carries the compressive load. Okay, and found in buildings supporting beams, floor, and roof. Okay, so you know that. So just to recap, just to show you some different arrangement configuration of columns, right? So basically, when you have columns, not necessarily you need to have beams, right? So there are many different type of construction system. So depending on which system that you use, but for this class, basically we use beams and columns in the construction, right? Because most of the, I think it's the most common construction system that we use, especially in Malaysia, okay, to use column with beams. But as you can see in the images, you can have columns without beams, right? Or what we call as flat. In this system, we call it flat slab system, right? So you don't have any beam connected to the column, but the shape of the column should be different, would be different from the normal columns. Yeah, you can see that there's a what we call as capital, right, on top, which replaces the function of beam, for example. Okay, so this is column supporting slab, directly supporting the slab without any beams. You cannot see any beams here. And then this is the usual one, column supporting beams. Okay, so basically, um, it's not that the beam sits on the column. Okay, so you have this column from the ground all the way up to the roof, but the beam is actually connected to the column. Okay, so all the load carried by the beam is transferred to the column. Okay, it's not that you have one column here and then beam and then another column sitting on the beam. It's not like that, right? Because the column is the main structural members that brings down all the loads from the top to the ground. Okay, so basically the beam is only transferring the load from each level to the nearest column. And then you can see column supporting roof, right? So and then this is also column supporting roof, right? So there are many configurations. So when you do your design in architectural design, um, I hope you are not confused whether the you can have column directly supporting the roof, right, without having any slab and so on. Okay, but you need to understand how the column works, whether you can have like a slanting column, because I think among architecture students there is a tendency to have like slanting columns, right? So to make your design more interesting. Okay, so we can have something like that, but normally we call it a strut, right? But as you can see in these images, um, on the configuration of struts, okay, so strut is a structural member in any position and carrying an axial compressive load. Okay, um, normally it would be symmetrical in shape. For example, like if you have one strut on this side, okay, so you would have another one on the other side, okay, to make the structure balance. Okay, so and also to transfer the load evenly. For example, like the load that these struts are supporting are actually coming from this over bridge, okay, pedestrian bridge. So some of the load is transferred to this side, another one to this side. Okay, and if you look at this as well, okay, you can see it's actually symmetrical balance, right? You have one strut here, another one over there, and here also. Okay, it's quite symmetrical except for this one. But in this case, you can see that uh, there are a few different columns and struts here. So for example, like this one only supporting this side, but you have another one which is actually um, symmetrical in the middle. Okay, so supporting both sides of the roof. And actually, this is not the real roof. This is just like um, artificial. Okay, so this is just like ceiling. So the load is basically not that high, okay, compared to the real roof. So that's why you can do something like this. But for you to have this kind of columns, okay, this kind of strut supporting the real roof, okay, for example, like this roof over here, okay, or maybe supporting floor structure, right? So basically, you can't do something like this. At least you need to have this shape. So meaning that instead of having a straight column supporting the slab or the roof, you can actually have something like this. Okay, so to make your design more interesting, maybe later in your final design in semester 4, you can explore something like this. So meaning that not necessarily you need to have a straight column, especially when it comes to the entrance. Okay, to enhance the appearance of the entrance, the front facade, you can try something like this, right? So it doesn't have to be straight, but you can't have only slanted in one direction like this. So normally, if you want to do something like this, you need to have one column goes up, okay, straight up to support the load, and additional struts, okay, supporting the other side, okay, something like that. And you can see from in this image, again, basically it's symmetrical. This one is supporting the roof and the ceiling. Okay, you can see that you have two sides, right? Okay, I'm not sure whether in the Beacon class you have been shown all this, right? But basically, if you read different books, they would come up with different um, things, right? Types of column might be, they might be showing different things when you look for types of column, right? But just to show you three different types of column. One is simple member with uniform cross section, simple member not with non-uniform cross section, and also build up columns. Okay, simple member with uniform cross section is basically the normal columns that you use, right? So not necessarily rectangular shape, not necessarily concrete or timber. It can be in any materials, using any materials. It's just that uh, the type is basically differentiated by the shape itself, right? So normally in timber, in concrete, the shape will be more or less similar, right? Either rectangular shape, square shape, or circular, right? But then when you look at steel section, steel columns, then you can see a variety of shape or the section of the column. Okay, so this is the most common type of column that you use in buildings. And for optimum performance, you need to have high mass of material in the direction where buckling can occur. So this one, there's another section on this. Okay, example of simple compression members or simple columns. It can be the normal I beam like this. Okay, as long as the shape is uniform, right? It doesn't matter whether it's I, H, square, rectangular, circle. Okay, or it can be like this. Okay, these are all simple member with uniform cross section. Okay, circular hollow section is the most suitable as it maximizes this perimeter in all direction. Okay, basically, um, it's actually the I would say the best shape of column. Right? It's just that connection is a bit difficult, as you can see, especially in steel columns. Right. So to make this kind of connection, for example, like this is your column, and then you have let's say roof structure using tube, steel tubes like this. You want to make the connection, so you have to cut before you can weld all the parts. You need to cut at certain shape, right? So it's not as simple as cutting like this and then you connect. It doesn't work that way. So you need to cut like maybe a bit curvy at certain parts, things like that. But so it's actually quite expensive to make that. Okay, to cut in that shape. So it's very difficult and very difficult to design, and the connection is expensive. Okay, square, rectangular, hollow section, good geometrical properties. Connections are easier to design, so that's why most of the time you can see in buildings you use this kind of section. Okay, this kind of column section. Hot roll section, for example, I or H section are the most common cross section used for compression members. Okay, because the material or the component is manufactured that way. Okay, so it's already in I shape, so you can straight away use that shape to become a column. Okay, another example, another type of column is simple members with non-uniform cross section. Okay, so in this type of column, also there are a few different uh, arrangement or different types. Okay, so the first one is tapered members. Okay, the cross section geometry changes continuously along the length, usually concrete column. So you can see from the image here, um, tapered meaning that one side smaller or bigger than the other side, right? So meaning that the shape is not consistent from ground to the top. Okay, compared to the previous one, basically if you cut the column at any parts, right? So in the previous one, when you cut, basically the size, the diameter or the length of the column are the same for wherever you cut. But for this type of column, because it's tapered, the size are not similar from ground to the top. So basically, when you cut at the bottom, the size is bigger compared to when you cut at the top. So it can be in both ways, not whether smaller on top, bigger at the bottom, or bigger on top, smaller at bottom. So this one is more for aesthetics, I would say. Okay, because the efficient part of the column is still this here until here, right? So meaning that the bigger part on the side, actually, if you remove also doesn't matter, right? So because the efficient part is actually the same size as this, going down to the ground. That's what you need. Right? So here also same. Basically, the efficient part is the smallest part lah. If you remove the bigger part here, also doesn't matter actually. So it's more for aesthetic. Okay, steel tapered members can be formed by welding together two reverse half of a hot roll H or I section whose web is cut. So meaning that this is normal I section. You cut in the middle, but you cut slightly slanted like this. Right. So basically, um, you take one part and then you rotate to the other side, right? And then you connect again. You get that shape, right? So basically, it becomes a tapered members as well, or it can be something like this, okay, depending on the what shape you want. But again, it's aesthetic, right? Okay, so another type of column with non-uniform cross section is basically what we call as step columns. But normally, this kind of column we use for industrial building, like for factory, for um, gudang, or what gudang in English? Warehouse. All right. Okay, thank you. Okay, so the cross section varies in steps, right? So it's different from the tapered members, because in tapered members, basically the cross section actually gradually increase or decrease from ground to the top, right? But in this type of column, basically um, it varies at only certain part. For example, like at the bottom here, when you cut, they are all the same. You cut any section, and at the bottom here, it's all the same until it reaches the upper part of the column. Okay, so when you cut this part, so basically it's smaller than the lower part. Right, usually found in industrial building with overhead traveling cranes like this. Okay, because the purpose of that step column is basically to put the like another beam so that you can put this crane on top, right? Just to allow for the crane to move on top of the structure. Okay, so it can also be used in multi-story buildings to resist the loads in the columns at the lower levels. Show you the example. Okay, so previously is in industrial building, and this one also in industrial building. So most of the time you can see this step columns in industrial building. But you can also use it in normal building actually, because if you understand how column works, basically, as I said, column would actually transfer the load from the roof to the ground. Okay, so it will accumulate the load from the roof. Okay, as it goes down, let's say you have a 4-story building, and then the roof. Okay, so the load from the roof is transferred to the column, and then below the roof, basically you have the fourth floor. So the column at the fourth floor, for example, let's say this is the fourth floor, right? So the column at this level basically only carry the load from that floor, and as it goes down to third level, so basically this column is actually carrying the load from this floor and the roof. Okay, so as it goes down, the more load it carries down to be transferred to the ground, right? So that's why actually when you design a column, you can actually have something like a smaller column on top like this, okay, and then bigger columns at the bottom, right? So it depends. If let's say, I think in this case, basically, if you use the tapered members, right? So that one is actually quite appropriate because the load is actually smaller on top, and as you go down, it becomes bigger and bigger at the bottom. But normally for ease of construction, we just use the same size from ground to the top, because you need to use, especially for concrete structure, right? Concrete construction, you need to use the formwork, right? So you basically just use the same formwork, this same size of column from ground to the top, right? But actually, the load that it carries on top is smaller than the load that it carries at the lower level. Okay, so as you can see from here, so it's same. So you have bigger column, but in this building, basically the function of the step column is more or less like this. There's something here, right? So there's a crane or something. So that's why you use step column basically to allow for this structure to sit on the beam or something like that. Right? Okay, another type of column is build up columns. Okay, so build up columns basically normally using steel component. It's fabricated from various different elements, as you can see from the image here, right? So at the bottom, basically looks different. Okay, so the size could be the same from ground to the top, right? It can be, let's say, 600 or 400 by 400 from the ground to the top. But if you look at the design like this, right? So the the bottom part could be different from the top part. Okay, so this is again for aesthetic purpose, right? So the most basic column would be the simple one. You don't need to have this kind of things, right? But for aesthetic purpose, just to give some kind of industrial feeling to the design. So you can, as you can see, I think probably this is a mall or something. Not necessarily. I don't think it's a mall. So maybe like, I don't know, maybe museum or something. Okay, so just to give some feature effect in the building, so you can have something different. So you can use this kind of column as well. So it consists of two or more main components connected together at intervals to form a single compound member. For example, I section list with small U section, or U section button with flat bars. Right? So these are flat bars. Okay, so this could be I section. Right, the main component is the I section, and you have steel plates, okay, steel bars, okay, bolted to the main component. So examples of build up columns in buildings, you can see it can come in different design, right? So these are the main components, and you add up other components, either minor components to the structure. Okay. Uh, so and for this kind of column, build up columns, you can also have something like step. Previously I mentioned about step columns, but the previous one is just a simple I section column you put together, okay, becomes step column. But in this case, basically you have a step column, but using this build up method. So you have different steel components to make up the. But again, the function is more or less similar to the previous step columns that I've shown. Right, basically you have for industrial building where you have overhead cranes, so you want to put the cranes on the column, so that's why you have that kind of design. Okay, so if you look at this column, basically, so only this part is already necessary to support the roof, because this part would go to the roof, okay, to support the roof of the warehouse or right, industrial building. Okay? But you need this because this part would actually carry the load of the crane. Okay, as you know, the crane would carry loads, right? Maybe lifting up certain goods or items, right? So it's quite heavy. So basically, this part of the column would do the work to transfer the load from the crane, okay, to this beam, and then from the beam to the column and to the ground, right? But for the purpose of supporting the roof itself, you only need this column. Okay, you don't need a huge column to support a roof, basically. Okay, because as you know, roof are not that heavy compared to other components. Okay, classification of columns. Okay, so basically we have three different classification for columns. You can have long columns, intermediate length column, and short column. Okay, so you can see from here, columns having length more than 30 times its diameter or slenderness ratio. Actually, there's a formula for slenderness ratio, but that one is too technical. It's too civil engineering, right? So basically, what you just remember this thing. So columns having length more than 30 times its diameter is considered as long column. Okay. So for example, like if I draw, let me just draw. Okay, if I draw a column this tall, right? So at a glance, or maybe by looking at the height itself, you can consider this as short, right? Because it's just like maybe just less than 1 meter, right? But if you include the length, the diameter of the column, okay, So by dimension, it might be short, right? But when you put diameter, if the diameter is just that big, right? Assuming that it's 30 times of the I mean the height is actually 30 times the width, then it can be considered as long column, even though the dimension is actually short. But when you put the diameter of the column, and the diameter is I mean the height is actually 30 times, more than 30 times of the diameter, then you can classify that as long column. Okay, so it does not depend on the measurement, okay, of the column itself, right? The measurement can be short, but if you compare with the diameter, right, and and when you compare, you get more than 30 times. I mean the height is more than 30 times the diameter, and then you can consider it as long column. Okay, so similarly to other uh, classifications, so intermediate length column having length between 8 to 30 times its diameter, and short columns having length less than 8 times its diameter. Okay, so you can have something for this one, for example, right, as opposed to this, you can have something like very very tall, 3 meter or 6 meter, but then when you look at the diameter, right, of the column, let's say the height is actually just less than 8 times of the diameter, then even though it's quite tall or quite high, but by this classification, by this formula, we can classify that as a short column, right? So I hope we can remember this thing. Okay, so for long column, basically it's stable when provided with lateral restraint. Okay, lateral restraint, something like beams or floor. Okay, so if you have a long column, okay, and then you have beam in between, basically it would make the column more stable compared to if you have only one column all the way go up to the roof, right? So this is considered as a single column. Okay, so similarly to your assignment, when you do your assignment, so that's why basically from the ground to the roof, if possible, all the columns should be at the same position, right? So from the ground to the roof, the column should be at the same position, except for maybe certain areas. For example, like maybe from the ground, above the ground floor, you have let's say balcony. So basically, the column from the ground floor it just stop at the balcony, and then above the balcony, there's the column that doesn't go up to the roof. Okay, that one is possible. So that is considered as one column, but in the case where the column is from the ground and all the way up to the roof, so this is considered as a single column. Okay, so it's not like this is one column, this is another column. Okay, so basically in the assignment, what you need to do is to identify two columns, right? One is intermediate, right, column, intermediate, or what did I mention? Okay, so basically the column within the building, right? So another column is perimeter columns, right? So column which sits at the perimeter of the building, basically, right? So even though it's just two column, but the two column basically runs from the ground all the way to the roof. So basically, you need to analyze for each level, right? So afterwards, I'm going to show you an example how you should do it, right? So from ground first and the roof. So you need to consider all this level and all the loads from this different level, and which would be carried by the column, right? Because in some cases, basically when you produce your design, you might want to do something like this. Okay, so especially if you have curtain wall or something, or maybe in an off in certain building, you want to have like double volume, triple volume. Okay, so in that case, basically you're gonna need a long column, okay, from ground to the roof, right? But make sure at certain intervals, for example, like let's say from the ground and here, maybe there's no floor slab connected to this column like this, right? But at least you have a beam, just the beam connecting from one column to the other column, right, to make it more stable, right? So example of this kind of column you can see in block A, right? In block A you can see that there are a few columns from level 1 up to the roof at level 5, okay, above level 5, okay. And I'm not sure by calculation I'm not sure whether it's considered as a long column or medium size, because you need to know the diameter, you need to know the dimension of the column, the height and the dimension of the section of the column, then only you can classify. Okay. So if let's say the same column, so one with lateral restraint like this, you have a slab and beams like this, and another one without the lateral restraint. Okay. If let's say two of the same loads, okay, same amount of loads, um, uh, for example, like let's say 100 kilonewton. Okay, maybe this column can only support um, ngam 100, right? 100 kilonewton. Okay, so if you have restraint for the column, basically it's going to be stable like this. Okay, but if there's no lateral restraint, okay, there's a tendency for the column, okay, to deform or to bend, okay, or to break like that in that shape. Okay, short column stable if loaded within design limit. Okay, whatever you do basically, and everything will be stable if it is loaded within design limit. Okay, even the beams or trusses, as long as the components are designed, the loads are within the design limit, it would be stable. Okay, so in this case, also the same. It will be stable if loaded within design limit. A failure occurs through crushing if heavily overloaded. Right. So normally, if as you know, each structural members basically they are designed to cater for certain amount of load, right? Um, you won't design anything. You won't design a structure um, to sustain everything, right? So there is a certain limit that you design. If you still remember the first lecture I mentioned, there is a safety margin in design. So basically, if let's say the structure that you design basically is to cater for uh, 10,000 kilonewton. Okay, 10,000 kilonewton. So the structure itself is designed to cater for that. So anything above that, okay, but 10,000 is the actual amount of load that you want the structure to carry. But considering the safety factor, right, there's a calculation that I show in the first or second week. Okay, so even though the load that you want the structure to carry is 10,000 kilonewton, but the actual design of structure should be more than that. It could be, let's say, to cater for 15,000 kilonewton, right? So there's a safety margin for that. So all structures are designed like that. So there's a certain safety margin for the structure. But if the load is greater than the safety margin itself, right? For example, the safety margin is 15,000 kilonewton, but the load is more than that, maybe 20,000 kilonewton, then eventually the structure would fail. So in this case, for the column, it might crush. So when it crashes, basically the shape is going to be something like this, right? So this case might happen during earthquake. Okay, because during earthquake, basically a structure is designed to cater for example, like if let's say this is not sure whether, most probably this is a building, right? Or maybe if you look at highways, you have columns at the highways. So basically the columns were designed to cater for the maximum amount of for example, on highways, the maximum amount number of transport, okay, cars, lorries, whatever, on the road itself. Okay, but during earthquake, basically you add up to that, so you already have load from transport, from cars, lorry, and so on. But due to earthquake, it actually putting more loads to the structure. Okay, so that's why in the end it would crash like that. Or maybe the ground is not stable, and then that could possibly another reason for the column to crush. Okay, compressive force, axial load is a load applied through the center of gravity of a column cross section. Okay, there are, basically there are two types of compressive force. So one is axial load. So another one is eccentric load. Axial load is load applied through the center gravity of the column cross section. Okay, so you have, let's say this is the column, right? So the load is actually applied to the center gravity, center of gravity of the column. And eccentric load basically, it's not at the center. It applied at any other point on the column cross section. Okay, this is the cross section. So the load could be applied to maybe just one side of the column. Okay, compressive strength can be measured using compression tests. Okay, I think probably this one in Beacon 2, maybe you have been shown something like this. Okay, measured by plotting the applied force against deformation in a testing machine. Usually the tests are made on small specimen in cube or cylinder shape. So this is more for civil engineering workshop. Okay. Okay, critical load. Basically, when you gradually increasing the load on the column, okay, the column would reach the ultimate crushing stress, or what we call as critical load, right? So as I mentioned earlier, basically each column. So this is just example, right? So I mean, I think the one of the easiest example is something like this. Okay, so you imagine that this can is a column, right? So if you push down the can with a very mild, not so strongly, okay, basically you won't change the shape of the can, right? So you would maintain like that, or maybe if it's slightly compressed a bit, but as you release your hand, it might go back to the original shape, right? But if you push more and more, you put more load and more load to the can itself, then there's one point where the can would actually become like this. It would crush. Okay, so similarly to column, right? So if let's say the load is within the design limit of the column, or maybe slightly higher, but still within the safety margin of the column, right? So it might be compressed a bit. It might go down. Okay. So in the case of maybe in concrete, you can't really see it because it's very rigid, right? It's very hard, so you can't really see. But if you take, for example, like timber, okay, or maybe a simple example would be if you have like a ruler, right? So a ruler, so you try to compress the ruler, okay. So if the load is still bearable by the structure, basically it would just bend a bit, right? But if you push more and more, it would reach the point where the ruler would break, no? Okay, so similar to this, and similarly to the to columns, right? So beyond that is what we call as critical load. So the point where uh, the the column or the structure cannot stand the load anymore. Okay, so and after that level, it would break. Okay, so that's what we call as critical load. Okay, beyond this stage, the column will fail by crushing. Okay, similar to this can. Okay. Okay. Sometimes a column fails by bending, right? So as I mentioned earlier, basically short columns, okay, because of the shape, because of the uh, ratio between the length and the height of the column is very little. Okay, so the most it can be, normally it would fail by crushing. Okay, so the column would be crushed down. But for long columns, and depends on what material used for the column, it might fail by bending or buckling like this, right? So let's say, imagine that this is a column, steel column especially, and if the load is more than what the column can carry, it might bend maybe some sideways like this, okay, or this way. So depending on which side the load coming from. Okay, it happens in the case of long column. Again, I mentioned short columns normally fail due to crushing. Okay, failure of a concrete column may be caused by insufficient number of spacing of horizontal circular ties. So in construction of concrete columns, right? Okay, before you pour the concrete into the formwork, so you need to arrange the steel bars like this, okay, reinforcement bar, and then you also need to have ties. So these are the main bars, vertical. You put it vertically, and you need to put the ties, okay, circular ties, right? So when the column is crushed, the column might crush due to probably there's not enough circular ties, okay, holding the main bars. So that's one of the possible cause of column crushing. So during earthquake, for example, earthquake shaking the ties fail to confine the concrete and the vertical reinforcing main bars. So example, this could be during earthquake. Okay, the critical load depends on these three things. So the first one is the length of member, right? So whether it's a short, medium, or long column. So normally, short column would have better, higher critical load. Okay, so for example, like coming back to this, if let's say this is considered as long column due to the ratio between the height and the diameter, and if you have another one with the same height but with greater diameter, right, or section, right? So obviously this would have higher critical load compared to this one. Okay, so that's why normally short, uh, it depends on whether it's a short column, medium column, or long column, right? So that's the first criteria. The second one is material properties. For example, yield strength. Okay, this is physics. So there are calculation for that. Elasticity of the material. Okay, for example, like if like plastic or uh, timber is more elastic compared to concrete. Okay, so it's like elasticity is something like plastic lah. Right? So when you compress or you push down, it would go back to the original uh, position, okay, original shape. And also due to section properties. Okay, so different kind of section of the column, right, would actually have different strength, in I mean when it comes to critical load. Okay, when an ideal column is subjected to compressive axial force, the only deformation that takes place is a shortening of the column. Okay, I've mentioned earlier. So basically, when you have load, okay, on top of the column, but again for concrete column you cannot see it because it's very rigid, very hard, right? So but basically there is some kind of compressive, I mean shortening of column, meaning that originally is that long, but when you put the load on top of the column, it becomes shorter, slightly shorter because of the compression above the column. Okay, and then an ideal column is one that is perfectly so basically when you release the load, it will go back to the original condition, original position. Okay, for low values of force, for if the force is very low, okay, if the column were to be deflected laterally, okay, meaning that when you have a force on top, okay, and then the column is already shortened a bit, and then there is some force coming from the side, right? It might bend like that. Okay, um, and then when the force is removed, the column would go back to the straight position. Okay, so that situation is indicated uh, by indicates a condition of stability or elasticity. So something like plastic, so you can actually bend, you can actually um, um, compress, and as you release the load, it will go back to the original um, condition. If the load were increased, okay, slowly you increase the load on top. Okay, so as you increase the load on top, the reaction force will be the same. Okay, as you know, whatever action on the object should be the same as the reaction force. Okay, so let's say you have increased the force, so the reaction force will be increased as well. It will be the same. Okay, um, so there is a point where it won't go back. If you release the force, it won't go back um, to the original shape, right? So it would remain in the deformed shape, or what we call as plasticity. Okay, so just now it was elasticity, meaning that the column, the structure is elastic. Okay, it can bend, but this one, when it cannot go back to the original shape, then we call it condition of plasticity. Okay, so this condition is referred to as buckling, and buckling is a failure mode, meaning once the column buckles, once a structure buckles, in this case column, or previously in beams, when it buckles, it doesn't go back to the original shape, then we can say that the structure already failed. Right? So not necessarily doesn't have to break entirely. Okay, it doesn't have to be crushed entirely, but as long as it cannot go back to the original form, original shape, then it is considered as I mean the structure is already failed. Okay, for a long column, buckling occurs way before the normal stress reaches the strength of the column material. Okay, for an intermediate length column, kneeling occurs when some areas give up before buckling. Okay, so another thing that influence the buckle shape. Okay, so earlier it was the condition things that influence the critical load. Okay, but this one is conditions that influence the shape, the buckle shape, how the shape buckle, whether it's like this, or it's like this, or slightly like that. But it depends on the condition of the end, the end condition of the column. Right? So whether it's fixed in one end, okay, pin in not in the other end, okay, or it's roller. Okay, this is a symbol for roller joint. So normally you don't use this for buildings. You normally use for bridges, kind of things, that kind of structure. Okay, so you have roller joint at one end, another end you have pin joint. Then the shape would become the buckle shape is like that. Right. So basically, this diagram shows the different buckling condition, okay, buckle shape of columns with different end condition. Okay, so most of the time, especially for buildings, you're going to have both ends fixed like this. Okay, so you have fixed column. Okay, so the top part of the column fixed to maybe floor or the roof, and then another part fixed to the lower level, to the lower floor. Okay, in this case, maybe in bridges, okay, in industrial buildings, you can have pin. So one pin. I think in this case, yeah, pin on the top and also pin at the bottom like this. So in this case, basically the bending shape, the buckling shape is like that. Okay, as simple as that. If you fix one end and another one is pin, yeah, to the structure, then the buckling shape is going to be like that. Okay, slightly different from this. And if you fix both, that's how it's going to be. Right? But again, as I mentioned, it depends on the material that you use for the column. Right? If you use steel, most likely, or timber, most likely you can see this shape. Okay, but if you use concrete, normally it's very difficult to see the buckling shape. Okay, and fixed free column. Actually, I don't know what kind of building you have. I mean, when do you use this kind of structure? Right? It looks like a flag post or something. Right? So one fixed and another one free. So I'm not sure in what situation you use this kind of column, right? But probably in industrial building or infrastructure building, you would have this kind of column arrangement. Okay. Okay, I think it's good enough if you just remember the buckle shape. Okay, depending on the position of the condition of the end of the columns. Okay, moment of inertia basically is very related to column design, but again, basically there's a very lengthy calculation formula to determine the moment of inertia and then to come up with the shape of the column, which is very difficult to understand. Normally, it's just for engineering students, right? So it's a property which measures the efficiency of a shape in respect of its resistance to bending. Okay, so different shape would have different resistance towards bending, even though the amount of material that you use for the material is the same. Okay, for example, like all this the blue parts, the amount, the volume is the same. Okay, but the arrangement of the materials is different. So they would have different resistance towards bending. Okay, so a shape is more efficient when the greater part of its mass is as far as possible from its center of gravity. So if you look at this section here, okay, if you look at all these three different sections, so that's the center of gravity right in the middle. Okay, so as you read this, a shape is more efficient when the greater part of its mass is as far as possible from its center of gravity, meaning that if the material is further apart from the center of gravity, that's the best actually. That's better than those column where you concentrate all the materials right towards the center of gravity like this. Okay, so meaning that if you compare this and this, okay, or this and this and this, right? So these two would have a better resistance towards bending compared to this one, okay, due to this moment of inertia, right? So for example, like column A, 400 centimeter square, column B, all the columns are 400 centimeter square, okay, but column B and C have larger moment of inertia than column A. Thus, they will be stronger or stiffer because of their area is spread out away from the center of gravity. Okay, so when you design something, but most of the time when you design building, right, because of constraint of space, um, I mean, of course, when you do something like this, your column will appear bigger than if you do this, right? But it's actually logical. It's actually you can actually have a column which is not solid like this. Okay, so you can have a hollow column like this. So the material, the concrete, is just around the center of gravity, right? But again, in terms of the formwork, it might be difficult to do, right? Because you need to have one formwork in the center, and then you have another formwork, okay, at the side. Then only you can pour concrete. Okay, compared to this one, you only need one formwork. Okay, maybe in terms of resistance towards bending, this is better, but in terms of cost when you construct, so this one you would need to construct this, you would need more formwork. Okay, formwork is made of normally timber, right? So you would need more formwork to do this compared to this. So that would incur higher costs. Okay, so that's why in the end you would end up with this normal column. Okay, but in terms of understanding how the structure works, you can actually have something like this. Okay, so that's why in the previous assignment when you do the integration, what so on, right? The feasibility, that kind of thing. So in the first assignment, one of the keyword is integration. Okay, so I think some of you actually integrated in the example in the lecture notes. Also, I mentioned I show example where you integrate column with downpipes, right? So it's logical, right? You can do that. You can have downpipe in the middle of the column, okay, because basically the material for the column is actually around the downpipe, right? Okay, the strength of a column may be increased by distributing the material as far from the center of gravity as possible to increase the moment of inertia. Okay, again, example, right? Compared between this and this, even though the mass of the material, the volume of the material is the same, but if you arrange them in different manner, so this would have more better resistance towards bending. Okay, at the same time, the material needs to be thick enough to prevent local buckling. Okay, so basically that there is a formula for that. Like you need to know how thick the material should be, right? If this is too thin, then it won't work as well, right? So you need to make sure that it's thick enough, that kind of things. But you don't have to worry about that. So just to understand the concept. So I section is much better in resisting bending compared to a rectangular section with similar cross sectional area. Okay, so in the future, maybe when you contemplating whether to use rectangular shape, okay, or I beam, okay, so maybe you can consider this thing moment of inertia, right? So um, so in this case, basically I section compared to rectangular section, square section. So you will have I section is better in resisting bending. Okay, now we come to the calculation part, right? Basically, this is the thing that you need to do for your assignment, right? One of the things that one of the two things that you need to do to in the analysis for your individual parts, not for the group part. So this is for individual part. So you need to analyze the two columns that you have chosen. Okay. So basically, there are two types of column load calculation. So there are two ways of determining the load that the column would carry. Okay. So the first one is beam reaction method. I believe in the previous few lectures you have learned about beam reaction, the calculation of beam reaction force, that kind of thing, right? Um, so it is related. So the first method basically relates to that, right? And then the second one is the one that we want you to use for the assignment, tributary area method, and also the one that might come out in the exam. Okay. So just a note. So basically, the minimum cross sectional dimension of a RC column is 225 times 225. So this is the minimum. So you cannot go smaller than this, right? Okay. So just show you the first method. Okay, beam's reaction method basically it collects load from adjacent beam ends. But if you do this in the calculation, it's going to take forever to finish, right? So just imagine that you have this column. So you need to use the formula that you learn in the beam topic, a beam reaction method. So you need to know, the load carried by the beam. Okay, so if there's a brick wall, right? So you need to know the load from the brick wall, self weight of the beam, and then the slab self weight. So whatever that you need in the calculation of beam, right? Because in the end, all of that, the first thing you do is basically to analyze the beam until you get the reaction force. Then that reaction force would be, for example, like if you want to analyze this beam, it would carry the reaction force from this beam, and also from this beam. Okay, so you need to tackle all these three beams. Okay, so in order for you to tackle this beam, you need to tackle this also. You need to know the load from this beam. So how much load it transferred to this beam, then only you would know the reaction force for this beam, right? So you need to know these three. But this is only one level. Okay, so you have ground level, you have first floor level, and you have the roof level. Okay, at least these three different levels. Okay, so you just imagine how much time you need to analyze the column, to know the load on the column using this method, right? So that's why we don't encourage you to do that, right? Yeah, we don't want you to kill yourself with too much calculation. Okay, so which beam contributes to the column load for column C1? Okay, already mentioned just now. So basically the reaction force at this point from beam B2, and reaction force from B1, and reaction force from B3. Okay, so for this column, basically it only come from B5 and B2, right? But you need to calculate the reaction force for all the beams. Okay, so which beams contribute to the column load for C1? Again, okay. So using this method, basically, so all the beams connected to the column, right, would be considered, would contribute to the column load for C1. Okay, so in this case, the reaction of beam B2 on this side, reaction of B4 on this side, reaction of B1 on this side, and reaction of B3 on this side. So you need to know these four reactions to determine the load of the column. Okay, so it's very tedious process to calculate that. Okay, so maybe you can take out a piece of paper, try to do a simple calculation. Okay, try to exercise your brain a bit. Okay, okay. So please remember back whatever you have learned in previous topic. For example, like slabs, right? Before this, you have learned about slab. Okay, uh, it's kind of trick question, lah, right? It's a kind of trick question. So, um, yeah, try to solve this. Okay, all right. So, assuming that, okay, calculate the column load for column C1. Assuming that the beam self weight is 10 kilonewton per meter, 10 kilonewton per meter. So, yeah. Okay, so you don't have to. I know that in the previous topic in beams, you learn about the what ultimate load, ultimate load lah, whatever. But you don't have to consider that. You don't have to multiply with that 1.4, 1.6 to calculate. Okay, so just use any information that you have from this image. That's it to derive um, with the total load. So in the exam also same. So if let's say the figures are not given, okay, we don't ask you to calculate the ultimate load. You don't have to you don't have to multiply with the ultimate load factor. Okay, try. Give you maybe 5 minutes. Okay, anyone got the answer? Huh? Not yet. So what's the answer? Anyone wants to try? Or you just pretend that you do the calculation? Okay. So don't worry, the exam question won't be like this. Okay. It will be simpler, che. Much simpler than this. I bet. All right. So okay, I think I just show you the okay before that, huh? So before you consider the calculation, right? First, you need to look at the load on the slab. So basically, this 100 kilonewton is the load, the total load of the slab itself, because you see the unit, right? So it's in kilonewton, meaning that the load, the total load of the slab. Okay. So normally, I think last time in the calculation of in the beam calculation, the unit normally for slab we use kilonewton per meter, right? So in that calculation, but in this case, because it's just a 3D image like this, so I just put the total load of the slab, okay, and then this is 150 kilonewton for this level, for this slab, right? Okay, now, so what kind of slab is this? Is it one way slab or two way slab? That's the first consideration you need to know, okay? Because if one way slab, then the load is only transferred to this beam and this beam, to these two sides, okay? If two way slab, then some is transferred to here, some transferred to this, some transferred to this beam and that beam, okay? But basically from the image itself, I already given you a clue lah. So basically, this is the to show that it's a one way slab, right? So when you divide 5, okay, divide with 2, so you get more than 2, right? So you get more than 2, so it's a one way slab, if you still remember lah, right? Okay, so how to determine one way slab or two way slab is like that, right? So divide, if you divide between the longer side, okay, ly divide by lx, and then get 2 or bigger than 2, I think 2 or more than 2, then it's a one way slab. If it's less than 2, then it's a two way slab, okay? So if you divide this with this, you get more than 2, so that's why it's a one way slab. So because of it's a one way slab, then we assume that the load from the slab is only transferred to this beam and this beam on the other side. So 50 goes here and 50 goes over here. So assuming that this beam is not carrying any load from the slab itself, so it only carries the self weight of the beam itself. Okay, so the load of the beam is 10. Okay, 10 kilonewton per meter, right? And you also have the dimension here, right? So 10 kilonewton per meter times 2 meter, so the total load is 20 kilonewton for the beam, right? So for the beam itself is 20 kilonewton, right? So 20 kilonewton. So the reaction force is basically half lah, right? So if this is 20, the total load of the beam is 20. So here should be 10, here should be 10. So you get B1, reaction force at RB1B is 10, and then here because the load is 50, here is 50 kilonewton, right? The total load of the slab, you don't have to multiply with 5 meter anymore because it's already the total load of the slab. So this is 50 plus this is 10 times 5 meter. 10 is the load of the beam times 5 meter. So 50 kilonewton for the beam. So 50, half goes that side, 25. This is 25, right? So um, sorry, right? So you total everything, and then you do for the lower level, right? RB3A. I think there's something wrong here, right? So by right, this is 50, 50 plus 50, 100. Betul lah, right? 100. Okay, 50 plus 50, 100. All right, so this is 50, this is 50. Okay, and then you do the same for this level because the length of the slab is the same. So this is also one way slab. It's just the load of the slab is different. Okay, so you total everything. So the total column load for C1 is 132.5. So anyone got this correct? No one, right? I believe no one. Sorry? Sorry, the what? FB is force. This is some of force from B. So it's just the naming of the in the calculation. Okay, so you can actually put any name lah, but normally we put like that lah. FB1. Any question? Do you have any question? You want me to repeat again? Which part you lost actually? Huh? Which part? Or you would rather ask your friend afterwards? Okay, I think because I think we are running out of time, so I need to go to the next one. Okay, so this is the method, the second method, the one that you please pay attention because this is the one that you're going to use for your assignment, and it might come out in the exam. So the second method of to calculate the column load is by tributary area method. Okay, talking about what? Kuih Raya, Baju Raya, dah siap. Okay, tributary area method. Okay, this is much more simpler than the first method where you don't have to calculate each reaction force from each beam connected to the column. Okay, but you just calculate the area of the around the column. Okay, so half distance of slab to adjacent column, also known as column area method. Okay, column load is equals to area of slab xy. This is x. This is y. Okay, xy times the load factor. Right. For example, if live load, you know that live load there's a live load factor, 1.5 for residential is 1.5 times the area. Then straight away you get the live load of that will be distributed to the column. Okay, so what it means from here, half distance of slab to adjacent column, meaning that you look at the two columns. Okay, look at you look at all the columns, right? So half distance between the two column. Okay, between, let's say this is 5 meter, so half distance is 2.5, which is somewhere here, right? And then between these two column, half distance, let's say this column is 4 meter, half distance is 2, right? So this side also same, 4 meter, half distance is 2, and this side is 3 meter, half distance is 1.5. Okay, so that's how you determine the tributary area for this column. Okay, for this one column, if you're looking just for this one column, right? So in this case, basically we assume whatever components within that tributary area, right, whatever load within that tributary area would be distributed to the column, right? So for example, like in this area you can see slabs, right? There are slabs. Okay, there are slabs, these are slabs within this area, and also there are beams, right, within that area, and also the column itself. Okay, and then if let's say you have brick wall within that area, so all these are actually considered in the calculation of the column load. Okay, calculate the shaded area of the slab. Okay, so in this case, x is so this side is 2 meter. This is 2 meter. So x is 4 meter. Y is uh, this is 2.25. 2.5. Yeah, this is wrong. This is 2.5. Yeah, this should be 2.5. This should be 1.5. Okay, so this is slightly different. Okay, so you get the dimension correct, and then you multiply with sorry. So in this case, you just calculate the area first, right? So this is just the area shaded, the shaded area. So you haven't include the load factor yet. Okay, in this case, okay, calculate x and y. So what is x? What is y? Okay, assuming there are half distance, half distance from the between the two columns. So what is x? Huh? X. X. What is x? 5. Okay, y? Huh? You use calculator or just congak? You got calculator, use calculator. What is y? Hurry up, hurry up. Y, y. What is y? The length of y. No response. 6.25. Okay. Right. So the area of the slab, the area of the slab, what's the area of the slab? 31.25. Okay, 6.25 times 5 is 31.25. Right? Okay. Uh, okay. Okay. You should be proud of yourself. Okay. Okay. So I hope you understand how to come up with this. Okay. But of course, the example that I show you is very simple, straightforward, right? So I believe when you get the floor plan, sometimes it won't be as simple as this, especially not for the whole building, probably for certain parts of the building where the position of the columns won't be as aligned as this. So you can have something like here the column will be like this, then down here maybe the column slightly different. So maybe the position of this column is slightly off. It doesn't follow that grid. So that might be this situation as well. So how you deal with this situation is basically to look at the column one by one. For example, like for because in the end you have to do the tributary area for the whole building, not just for the column that you choose. But first, as a group, you need to do the tributary area for the whole building, just like my example afterwards. Um, then only you choose, okay, which column that you want to work on. Okay, I think this is a good example also because the position of columns are not all aligned. Okay, so on this side they are aligned. Okay, this is aligned. But when it comes to this part, slightly different. Okay, so you have column here, but here the column is between here and here. Right, the distance is longer compared to the top. And again, at the bottom here, it becomes similar to this again. Okay, so you see how to do that. Right. So the first thing you need to do when it comes to the column analysis, which is a group in a group component, you need to come up with, after you produce the structural plan, you need to come up with the column tributary area. Okay. So once you have plot the position of columns for your building in the assignment, you need to draw the tributary area. Okay, for each level, so ground floor and first floor. I think if possible, try not to do like 3-4 floors, right? So you just take, even though the plan that you have is for 3-story or 4-story building, okay. But to make your life easier, I think just take 2 levels, okay. Because if you put there 4 plans, you need to produce all the 4 structural plans. Okay, so I think just take 2 plans as long as there are enough for each one of you to choose the beams for each group members. Then that should be okay. Okay, so just take 2 plans, ground floor, first floor, and the roof, and then straight away produce the structural plan. Okay, so in this case, for this kind of column position, okay, we look at it one by one. The first one is you look at level 2. Okay, So you need to identify the tributary area for each column on each level. Okay, so in this case it's level 2. Okay, name all columns according to grid lines. So how do you name the column? First, like this one, you look at the grid line. A, this is 1. Okay, A1, this is B1, C1. Okay, this is A2, B2, C2. Right, so B3, C3, this is A4. Okay, so you should name the column that manner. That's the reason why you have column. One of the reason why you have why you have the grid lines. Okay, so for ease of reference. Okay, in this case, you look at the two column. Okay, okay, half distance is, if 6 meter, then half distance is 3 meter. Okay, here also same. Yeah? And then in this case, slightly tricky, but you just look at the position of this grid. Okay, the vertical grid. Basically, the grid, actually you have these two grids, right? So you can still take this as the distance lah. Okay, between this grid and this grid. Okay, so it's still in the middle. So all here would be straight line lah. Okay, and then once you settle this, you look at the other part. So don't do the horizontal line yet. So the next one. Okay, so you look at this and this, this and this. Okay, half distance. And even though there's no column here, but the grid line is actually still aligned. These two are still aligned. So you can put it in the middle of the grid lines. So that's how you get that line. Okay, the next one. Okay, this is slightly tricky, because here you have columns, right? So you look at this, these two columns. The half distance is between this column and this column, and then you stop there. And then this part, you look at the column between this and this grid line. Okay, because you have another grid line here. So the other part just now, this is the same grid line. So here you have another grid line with column. So that's why you take the distance between these two columns. And then here you look at these two columns and these two grid lines basically. So for that part, the line is going to be slightly off from here. Okay, so you look at these two, then that's where your line is going to be. And then the next one is between these two. So the half distance between these two, then that's where the line is. And then the last one, okay, half distance between these two. So that's where your line is. Okay, so in this case, okay, the previous example I show, basically the tributary area is just square shape, rectangular shape. Okay, but it can be in different shape like this. All right, so this is rectangular, and then this is like L shape because there's no other column here, so it becomes L shape. Okay, this one also L shape. Okay, because of the shape of the plan like that. So the one in the middle, the one that I call the intermediate column or something like that. Okay, so would carry this whole area. So whatever component within this area would be carried by this column. So whatever component, beams, wall, slab within this area will be carried by this column. Okay, so each of the column would carry the load within that area only. Okay, so that's just the name of the columns. Okay, the next one, level 1, same. So you do the same. You look at the columns, okay, one by one. Then only you draw, right? Okay, so something like that. Okay, so in this case, because this part is cantilevered, so in case your building there's a cantilevered part, right? That there's a cantilevered slab at the edge of the building like this, then that would be considered within the nearest tributary area for the nearest column. So like something like this. Okay. Okay, then after you determine the tributary area, this is what you need to do. Basically, similar to beam. So you need to know the dead load, live load, okay, ultimate load. Okay, first, you list down all the load within that area. Okay, for example, like let's say this is just the factor lah. So when you do the calculation of beam, you would know the factor already. Okay, you know the concrete slab what's the weight of the concrete slab, what's the weight of the beam self weight, okay, brick wall. So you would have this when you do the first part, okay, when you do the beam calculation. Okay, so basically just take from there. And life load factor, normally for residents, the whole house, you just use 1.5 kilonewton, okay, per meter square. Right. So if let's say you want to know the column load for column A, right? So first you calculate the dead load for column A. So see how it goes. So first the concrete slab. So let's say this is the concrete. This is column A. So concrete slab is just the yellow part here. Even though the original, the whole slab is his, right? So this is the whole slab. So but you just take the one within the tributary area. So how to do that? You take the length, okay, 2 times 6, okay, and then times the factor here, 3.6, and then you get 43.2, and then beam self weight. So it depends on whether there is a beam within that tributary area or not. So in this case, basically, this is the beam length, 6 meter, 2 meter, 2 meter. So basically, the beam, I consider the beam here 6 meter, 2 meter. So there's a beam here, and also there's a beam here. But I only take half distance, so 6 plus 2 plus 2. But if you look at the overall dimension, actually it's not really logical to have like 12-meter beam from one column to the other column, right? So basically this dimension is not it's not practical, right? Also it's possible actually, but then not practical for a building, for a house. Okay, so 1.44 is the factor, right? So you just add up all the length, okay, 6 meter plus 2 meter plus 2 meter, so 10 meter. So multiply with the beam self weight, so you get 14.4. And then for brick wall also same, more or less the same as beam. Okay, so you just identify which part of the within the tributary area with brick wall. So for example, like maybe just this part, okay, 6 meter plus 2 meter, assuming that there's no brick wall here, 6 plus 2 times 10, so you get 80 kilonewton. And then column self weight. Okay, so basically column self weight, previously you haven't learned. Basically it's the dimension of the column itself times the length, right? So the section, okay, the length, the width of the column times the length of the column. Assuming that the column self weight is 6.48 kilonewton, you have to consider within that area as well, because the column itself is within that tributary area. So you need to consider the self weight as well. So the total dead load is 43.2 plus, so you total up everything, you get 144.08 just for the dead load. And then you have to calculate the live load, similar to beam calculation, beam analysis. You need to calculate the live load as well, right? So total live load is very straightforward. You just take the area, okay, the tributary area just now, 2 times 6, right? Just take the area, and then times 1.5. That's the factor for live load for residential building. You get 18 kilonewton. Then the ultimate load, so similar to beam. So first you multiply with the dead load, and then multiply with live load. Okay, so 1.4 and 1.6 that is the ultimate load factor, just like beams. Okay, so you total everything. So total column load for column A is 230.51. Okay, so basically that's what you need to calculate in your assignment. Okay, so column load in multi-story building. So just now is just example for one level, but when it comes to multi-story building, so just like the building that you use for the assignment, so you have to calculate the load from the ground to the roof. So that's why in the project brief, in the assignment brief, the load, the dead load and live load for the roof is given. If you look carefully in the brief, so it's given live load and dead load factor for the roof. So you don't really have to calculate the roof, because the load is already given. Okay, so you just use the factor. Okay, start the calculation from the highest to the lowest level. Right, so basically for the let's say you have this column here. So let's say this is the section. So ground floor. So basically you have the ground beam and the ground floor slab, right? And then first floor, you have first floor first floor slab and the first floor beam, and for the roof you have the beam. Okay, and the roof doesn't matter whether you use flat roof or trusses. Okay, so you just use the load factor given in the brief, right? Okay, but when you do the calculation, so you need to bear in mind that in the roof level, basically you just have the roof. You don't have to include the slab weight, right? So you only calculate the roof, the beam, and there's also no brick wall on the roof, right? So basically just the beam and the roof, right? And do that for the dead load and live load. Then you move down to the and another thing is when you do the load calculation for the roof level, you don't include the weight of the column itself because the column is below the roof. Okay, so when you do a calculation for this level, for first floor level, then only you include the slab, the beam, the column, and also if you have the brick wall. Okay, so into the calculation. So similarly to the ground level, right? So you total up everything, then that would contribute to the total load. Okay, so this is another example, but I don't think I'm going to show this. This is just to show a different why we put gymnasium is basically um, uh, the life load factor for gymnasium is slightly different from the other spaces. Okay, so just to show some difference. No? Um, but in your case, for the assignment, you just consider all the spaces for the life load factor for all spaces is 1.5. Okay, you don't have to take like kitchen, let's say 2.0, right? Bathroom 2.0, and then if you have a gym in the house, you put 4.0. So you don't have to do that. Basically, all 1.5 that will be you just do that. So you just put 1.5 for all the spaces. Okay. All right. I think that's all. Okay. Any question before you go for tutorial? Okay, so you can get the lecture notes from Times, right? So you can to understand better the calculation. You just download this notes. Okay, if there's no question, I see you in studio. Okay, so I wish Selamat Hari Raya to all Malay and Muslim friends. Okay, so have a safe journey home. Right? Okay, thank you. Can I get the attendance? Please sign the attendance.